So what we're doing today is 2-8. We're going to be modeling polynomials in real-world situations. We're going to just be using our calculator because if any of you go on to be mathematicians or statisticians, you're going to be able to use your calculator when you're doing stuff for companies in the real world. So that's how we're going to learn to do it today, which is going to be really nice because it's going to be quick and efficient and correct. So from now on, if you were ever asked to do something like this, you'll want to use your calculator because it's way quicker. On an APT, you'd want to use your calculator instead of doing it by hand. Okay, so first of all, it says polynomial functions can be degree 0, degree 1, degree 2, degree 3, and so on. We all know that. We can have polynomials of different degrees. You can use polynomial functions to model many real-world situations. The behavior of the graphs of polynomial functions of different degrees can suggest what type of polynomial will be best fit for a particular data set. So it says you can use a graphing calculator to help you find the functions that model the data in the table shown here. So everybody look right here. Here's some XY points here. If I said to you, what fits does this have? Is it linear? Is it quadratic? Do these points match a linear line, a quadratic, or a cubic, or a quartic, and so on? We can figure this out. So I want you to look. Right down here, I have plotted out those points. So do you see how I went over 0 up 10.1, over 5 up 2.8? Does everybody see how I've just plotted these points in this XY chart? Now look right here. If I draw a line, do you see how it doesn't connect the dots? It's not a very good fit. A line does not fit the data points very well. So it's not really a linear set of data here. Well, let's look. A quadratic, doesn't it look like a closer fit to you than a line? It's closer to fitting those points. Better than a line, but it's not a perfect fit. And then all of a sudden, when I graph it cubically, do you see how a cubic fits it perfectly, everybody? All good? Okay. So these are cubic points. They come from a cubic polynomial. So we can actually calculate that in our calculator, and we'll get to that in just a second. All right, so here's what's called the n+1 point principle. So let's read it. It says, for any set of n+1 points in the coordinate plane that pass the vertical line test. So first of all, what that means is if we have a bunch of xy points, to know the polynomial, it has to be a function. That's what it means by passing the vertical line test. So we can't have 2 points like this, because then it's not going to match any functions, because it's not considered a function. It doesn't pass the vertical line test. Does that make sense, everybody? Okay, so as long as we have a set of points that pass the vertical line test that are a function, there will be a unique polynomial of degree at most n that fits the points perfectly. Now it says this principle confirms that any 2 points determine a unique line. 3 points that are not on a line determine a unique parabola. 4 points that are not on a line or a parabola determine a unique cubic, and so forth. Does everybody see what's kind of working here? It says if we have n+1 points, then there will be a degree n that fits those points perfectly. Does everybody understand? So look right here. It says, what polynomial function has a graph that passes through these 4 points? All right, so these are 4 points. We have 4 points. So what degree is going to fit these 4 points perfectly? Degree 3. So this is going to have a degree 3 that fits the points perfectly. So everybody, I'm going to show you how to do that in our calculator. Instead of doing it by hand, like is what you would have had to do before this was set up a system of equations and solve, which would have taken forever. Now we're just going to use our calculator. So everybody pull up your calculator and follow me through this. There's a couple things you have to be absolutely certain before you start this. So everybody follow me. We're going to go to our catalog and make sure we turn our diagnostics on. So you're going to hit second 0. See how it says catalog. Now scroll down to diagnostics on, the word D, diagnostics on. Right there. We want our diagnostics turned on. Everybody hit enter. Now hit enter. And it's done. Hit enter and then hit enter. It says it's done. Okay, now that our diagnostics are on, what we're going to do is we need to tell our calculator what xy points we have. So you'll hit the stat key, stat, into edit. Stat, into edit. So is everybody with me? Hit enter. In list 1, you've got to type in all your x values. In list 2, you've got to type in your y values. Does everybody have list 1, list 2? If you don't have list 1 and list 2, you need to reset your calculator. Because that means you've accidentally went up here and went like this. You've gone up here, and instead of hitting clear, you accidentally went up and deleted a list. You've hit delete, and the list 2 is gone. You see the problem with that? So we need list 1 and list 2. Does everybody have list 1 and list 2? If not, do second plus sign, go down to reset, and reset your calculator. You're all going to have that happen to you on accident at once. Like, for example, if I hit delete right now, it's going to delete list 2 instead of clear, which would be bad. You see what I'm saying? Now watch. I can clear out this list by hitting clear. It doesn't do anything until I scroll down. So a couple things. Don't accidentally hit delete, or else it's going to delete the list. You need to reset your calculator. Okay, in list 1, type in all your x values. So my x values for this were 0, 1, 2, and -1. You do not need to put them in order. Your calculator will do it for you. So we're typing in 1, enter, 2, enter, 0, enter, and then -1. Now in list 2, you've got to type in the y values that match those x values. So we had x values of -3, -1, 5, and -7. Make sure you type in -2. -3. Okay. Good point. No, it's oh yeah, so 0, -3. Don't we have that? Oh, so I don't have this typed in right, do I? 0, -3. Okay, -3, -1, 5, and then -7, right? Okay, now these match up. So now you're gonna get out of here. Well, you don't even have to, but you can exit. So second quit, and then I'm gonna hit stat, over to calculate. So hit the stat key again. Instead of an edit, we're gonna calculate. Now we said it was a cubic, didn't we? Now look, for fun, I'm going to calculate the linear regression line to show you. We still can get a line, it's just not going to be a very good fit. Now I want to show you a couple things. So do you see how it gives you the form of a line, ax plus b? Then it gives you the a value and the b value. So this would be 3.8x minus 3.4. Now look at r squared. The r, we're not even going to use r for anything, but r squared is the percent of a perfect fit that this line is for those points. So do you see how this is 0.96? It's a 96% accuracy rate to those points. So that's pretty not bad, right? A line almost fits them. Do you see how 96% is pretty accurate? So, but watch, if you do stat, calculate, we decided it was cubic, it's going to be a perfect fit. So watch, cubic regression line, hit enter. It gives you the form of a cubic. It gives you what A, B, C, and D is, the coefficients. And r squared is 1. 1 is 100% perfect fit. So now we have the cubic, 1x cubed minus x squared plus 2x minus 3. No math involved. Yes. Because we use the n plus 1 point principle. If there are 4 points, then there'll be a cubic that matches those points perfectly. No, it's n plus 1 points. We have 4 points. Isn't n 1 less than plus 1? So the degree is 1 less than the number of points. Because you see how this is plus 1, this is n. So isn't that really n, like 1 less than the number of points? Makes sense, everybody? But now, let's pretend I forgot the n plus 1 point principle. And I did the linear regression line, the quadratic, and the cubic. How would I know to pick cubic? Because it was r squared 1. Does that make sense? So the n plus 1 point principle isn't, if you didn't remember that, it would not be the end of the world. You'd calculate line, quadratic, cubic, and then you would say, oh, the cubic's the perfect fit. I'm going to choose a cubic. Does that make sense? Okay, cool. So everybody, sorry, that wasn't a video. Okay. Let's do number 1. So it says, find a polynomial whose graph passes through these points. So you guys, you could be asked this is what you did by hand. If I said to you, back in the day when you were doing this back in like secondary math 1, if they said given 2 points, write the equation of the line, you could do that by hand. But now we know how to just use our calculator. You'd say there's 2 points, so what's the degree that we're going to use here? Yep, there's going to be a line that fits them perfectly. So you'll go to your calculator, go to stat, edit. Now once again, do not hit delete, hit clear, scroll down. Hit clear, scroll down. Okay, so our points were, this is number 1, type them in. Your x values are 4, -3, x is -1, and 13. Now you'll hit stat, calculate, linear regression line. Now look at that. So we now have the equation. Look, r squared is 1, so it was a perfect fit. So we would have the equation y is equal to -2x plus 7. That was a lot quicker and easier than doing it by hand, maybe, depending on who you are. So if on an ACT they said, given these 2 points, what's the slope? You could hurry and do this and say -2 to make absolute sure you don't get it wrong. Does that make sense, everybody? Yes. Yep, they do. That's why I require you to have a TI 84 or 83, because that's what they'll allow on the ACT. Okay, cool. Okay, let's do number 8. So once again, go to number 8. Now, once again, how many points do I have? 4, so there'll probably be a cubic that fits perfectly. But once again, we'll use whatever r squared's perfect 1, a perfect fit, or closest to 1. So we'll use a cubic for this one. So everybody go ahead and do it. So you guys do it. It's going to take me too long to do it up here. You guys do it, and then I'll write down the answer. Did we all get this?
No.
Did we all get this? Do you have any questions? Okay, cool. We don't have time to give you time to do 1 through 8, but everybody look up here. So this is where it becomes like in the real world, if a company came to you and hired you as a statistician, this is exactly what you do. So there are companies, they don't know how to do this. They can't think like this. So what they do is they say, their CEOs, they hire these mathematicians to come in and they say, I'm going to give you some data that we've had in the past. Now, can you tell me what you predict our company is going to be in the future? Like how much so for example, look right here. This company is it's a world gold production company. So this is their past record here. In 1985, they produced 49.3 million troy ounces of gold. And then in 1990, this much. And in 1995, this much. In 2000, this much. So what this company would do is say to you, given this data, how much can you predict of gold that we'll produce in the future? Does that make sense, everybody? So you would literally be getting paid a buttload of money to come in and just type it into your calculator. So let's do this. Now everybody, let's read though, because we've got to be careful. It says let x be the number of years after 1985. So how many years after 1985 is 1985? 0. So this is our x, this is our y points. This is 0. How many years is this after 1985? How about this? And then this? 15. So we've got to make sure we read because we've got to use the correct x value. So here we go. Go to your calculator. Now in the real world, they don't come out nice and pretty like this. In the real world, they don't come out whole numbers. That's just real world math for you. So stat, edit. Once again, in list 1, you'll type in 0, 5, 10, 15. And then in list 2, make sure they match up. Now let's go like this. Let's go stat, calculate. Let's calculate each, because we weren't told, were we? Well, let's go off of r squared this time to pick which is our best fit. Look, I'm going to calculate linear regression line. Do you see how it's 0.88, r squared? 88% is not a good fit at all. So let's move on. Calculate quadratic. Well, look at that. R squared is 0.93. 93% still not that great, because let's see if we can get closer. If that was the best, if that was the closest to one, we'd use that one. Well, let's check a few more. And I checked the cubic, and look, a perfect fit. Cubic is a perfect fit here, so we're going to go with that. So now look, in the real world, once again, it's not going to come out pretty. But that's okay. That's just real world math. So you would say we have a function, f of x is equal to 0.038 x cubed minus 0.956 x squared. We want to be exact, so we'll write out the entire decimal. Plus 8.01x plus 49.3. Now, why would we want this? Because isn't this equation going to allow us to generate now any? If I said to you, in 20 more years, can't I plug in for x and know what we can predict based on previous experience here? So now we can produce, we can answer questions. So what this company would say to you is, how much gold do you see us producing in 2010, for example? Well, what year should we plug in for x here? 20, wouldn't it be? No, it'd be 25, wouldn't it? Do you see why, everybody? 1985 is our 0, and so then 2010 would be 25. So we want to know function at 25. So we'll type in 0.038. Everybody do this. This is actually part of the assignment. 25 cubed minus 0.956 25 squared. You've got to use parentheses, plus 8.01 times 25 plus 49.3. So now we're predicting, based on their previous experience, how much gold they're going to produce in 2010. You type that in, and you get, I got 245, I think. Yes. So it is asking us that on a different problem. So let's just write it down. Yeah, it's number 15 on the back. So this is 245.8. And then we would say troy ounces, which is just how they measure gold. Troy ounces and troy ounces. I don't even know what that really means. But now, once again, that was not hard. And you're getting paid a buttload of money to come into this company and do this for them, which was not hard at all. Yes. No, I just made the answer. Okay, so then it asks you for a few years. Now, you could go back in time. Like, they could say, okay, we only started keeping records here because before that, our company wasn't very official. Can you give me what you think we made back in the day of 1975 when our first year was? Do you see how this could be helpful, everybody? They didn't keep records back then, but based on what we're seeing here, we can predict backwards. Wouldn't I be plugging in -10 for that, or -10 for that one? So we can now predict stuff in the past as well. Okay, cool. So that's all we're going to do here. Now look, I'm just going to read this one to you. On 13 and 14, it says, find a cubic and a quartic model for each set of values. Then describe which model best represents the values. You'll write out your cubic model, you'll write out your quartic model, and then whichever r squared is closest or equal to 1 would be the best fit, wouldn't it? No, write out the equation. Right? So let's do, we just did this one. I just wanted to do all in the same spot, so it made sense. It says estimate world gold production for this year, and this year. So you guys can continue that one. Now this is the last thing, and then the rest of the time will be yours to write. So it's called extrapolation versus interpolation. So you might see these words. So it says, when deciding whether a model is reliable, it is important to consider the source of where the data came from. Data generated by a law of physics or geometric formula will have a mathematical model that fits the data and yields accurate predictions from everything. But with other data, such as sales records, you can approximate the data only within or close to the domain over which it was generated. So what this means, guys, is if we're producing a polynomial for sales records, can we use that for maybe a different company's sales records? No, because we're using this company's information to get that polynomial. Does that make sense? So interpolation means you use the model, you use the domain only for the model that it represents. So it says if a polynomial is model of sales records for a phone company of Verizon, and you use that polynomial to estimate sales records for Verizon, it's called interpolation. However, if we went and said, okay, I'm going to now use that function and calculate Sprint, it's not going to necessarily be correct, right? We're plugging a domain in that has nothing to do with necessarily the domain we use. That's extrapolation. Using a polynomial with a domain that doesn't even work with it. Does that make sense? That doesn't relate. You understand interpolation versus extrapolation? Okay. Inter makes sense. Inter inside the domain. Extra is outside the domain. Okay, sweet. So you're going to finish the worksheet. Do not do problems 20 or 21. Just cross those out. The rest of the time is yours.